In April 2003, Boeing made an announcement that sent shockwaves through the aviation industry. It was going to build a wide-body airliner made primarily of carbon fiber composite, not aluminium, not the material that had defined commercial aviation for decades. Carbon fiber reinforced plastic. Specifically, no one had ever attempted this at scale. Not for a widebody, not for an aircraft that would carry hundreds of passengers across oceans for decades to come. Boeing was betting the future on unproven materials and a supply chain model so radical it would make their competitors question whether Seattle had lost its mind entirely. How did the world's most successful aircraft manufacturer nearly destroy itself trying to build the plane of the future? By the early 2000s, Boeing was losing. For the first time in decades, it had a real competitor, Airbus. The numbers told a brutal story. In 2003, Airbus delivered more aircraft than Boeing. The A330 was dominating the mid-sized widebody market. The A320 family was chipping away at Boeing's narrow-body dominance, and Airbus had just launched the A380, a super jumbo that promised to redefine long-haul aviation. Boeing's widebody lineup was aging. The 777 was successful, but it was a 1990s design and was slowly aging. The 767 was 3 decades old. The 747's dominance was slowly fading, and Boeing had nothing in development to counter Airbus's momentum across multiple market segments. Boeing faced a strategic dilemma that would determine the company's future. It could chase Airbus into the super jumbo game, building an even larger or similar aircraft to compete with the A380, or they could bet on a completely different vision of aviation's future. Initially, Boeing chose speed. In 2001, they unveiled the Sonic Cruiser, a sleek, delta-winged concept that would fly near the speed of sound, cutting transoceanic flight times by hours. It was technologically daring, visually stunning, and airlines wanted absolutely nothing to do with it. The problem was fuel. The Sonic Cruiser would burn significantly more fuel than existing aircraft to achieve those higher speeds. And in the post-9/11 aviation market, with passenger demand uncertain, airlines weren't interested in faster. They wanted cheaper to operate. Boeing's leadership, led by commercial airplanes president Alan Mulally, made a critical pivot. They took the advanced aerodynamics and systems work from the Sonic Cruiser and redirected it toward efficiency instead of speed. The market insight was clear. Airlines didn't want super jumbos feeding massive hubs. They didn't want Mach 0.95 cruise speeds. They wanted an aircraft that could profitably operate point-to-point routes that were too thin for a 747, but too long for a 767. They wanted to fly from Seattle to Copenhagen directly instead of connecting passengers through hubs in between, Los Angeles to Mumbai, without stopping in Tokyo. Boeing's answer would be the 7E7, later renamed the 787 Dreamliner. It would carry 200 to 300 passengers, it would have the range to connect any 2 cities on Earth, non-stop, and it would burn 20% less fuel than the aircraft it would replace. But here's what made the 787 truly revolutionary. Boeing wasn't just designing a more efficient airplane, they were fundamentally reimagining what an aircraft could be made of, how it could be built, and who would build it. The decision to use carbon fiber composites for half the aircraft's structural weight wasn't an incremental improvement. It was a complete departure from decades of aluminium construction. Composites offered extraordinary advantages: lighter weight, no corrosion, better fatigue resistance, fewer fasteners. But no one had ever manufactured them at this scale. No one had certified them for primary structure on a widebody. No one knew if the supply chain could even produce enough material. Boeing was about to find out, and the answer would nearly bankrupt them. The 787's airframe would be 50% carbon fiber reinforced plastic by weight, not just fairings or control surfaces, primary structure, the fuselage barrels, the wing skins, the tail assembly. This wasn't a materials upgrade. This was a complete reinvention of how you build an airplane. Carbon fiber composite is exactly what it sounds like. Thousands of carbon filaments woven into fabric, then layered with epoxy resin and cured in massive autoclaves under heat and pressure. The result is a material stronger than aluminium at a fraction of the weight. It doesn't corrode, it doesn't fatigue the way metal does, and it can be formed into complex shapes that would be impossible to machine from aluminium. The weight savings alone justified the risk. Every pound removed from an aircraft's empty weight is a pound of fuel you don't have to carry, or a pound of payload you can add. The 787 would be roughly 20% lighter than an equivalent aluminium aircraft. That translated directly into fuel efficiency, around 20% better than the aircraft it would replace. But the real advantage was what composites allowed Boeing to do with the passenger experience. Aluminium fuselages are built from curved panels riveted together. The curvature is limited by how far you can bend aluminium without cracking it. That constraint determines cabin width, window size, everything. Composites don't have that limitation. Boeing could make the 787's fuselage wider than a 767, despite similar external dimensions. It could enlarge the windows to 19 inches tall, 30% bigger than any other commercial aircraft. Then there was pressurization. Aluminium fatigues under repeated pressure cycles. Over thousands of flights, those pressure cycles create microscopic cracks. It's why airlines have to limit cabin pressure altitude to 8,000 feet. Any higher, and the fatigue accelerates dangerously and beyond economic sense. Composites don't fatigue the same way. Airlines could pressurize the 787 to a cabin altitude of 6,000 feet without compromising structural life. Passengers would arrive less dehydrated, less fatigued, with fewer headaches and less jet lag. The cabin could also maintain higher humidity, 15% instead of 4%, because there was no aluminium to corrode. These weren't marketing gimmicks, they were genuine improvements in passenger comfort enabled by materials science. The engines were equally revolutionary. Boeing offered two options, the General Electric GE-NX and the Rolls-Royce Trent 1000. Both were designs optimized for fuel efficiency. Both featured advanced materials, including ceramic matrix composites in the hot sections. Both promised double-digit efficiency gains over previous generation engines. The 787 would also be the first commercial aircraft to use electric systems instead of pneumatic for cabin pressurization and wing anti-ice. Traditional aircraft bleed high-pressure air from the engines for these functions, which reduces engine efficiency. The 787's all-electric architecture eliminated bleed air entirely, recovering that efficiency loss. Range was the final piece. The 787 would be fully ETOPS certified from entry into service, meaning it could fly routes more than 3 hours from the nearest suitable diversion airport. That opened up transoceanic point-to-point routes that had never been economically viable. Airlines could bypass congested hubs and fly direct. Boeing had designed an aircraft that was lighter, more efficient, more comfortable, and more capable than anything flying. On paper, it was a masterpiece. But here's what Boeing's engineers knew and didn't say publicly. Every single one of these innovations carried enormous technical risk. Manufacturing composites at this scale had never been done. Certifying them for primary structure would require years of testing. Integrating all-electric systems would expose any software flaws catastrophically. And Boeing was about to compound that technical risk with a business decision that would make the 787 the most expensive commercial aircraft program in history. The most radical gamble wasn't the carbon fiber, it was how Boeing decided to build it. Boeing's plan for building the 787 was unprecedented in aerospace manufacturing. It would outsource roughly 70% of the aircraft to a global network of what it called risk-sharing partners. This wasn't traditional subcontracting. Boeing was transferring both the financial risk and the engineering responsibility to suppliers around the world. These partners would fund their own development costs, design and build complete aircraft sections with systems installed, and only get paid when Boeing delivered finished aircraft to customers. The financial logic was seductive. Boeing could build the 787 without shouldering the entire development cost. Risk would be distributed across dozens of suppliers, and if the program succeeded, everyone would profit together. The global network looked impressive on paper. Alenia Aeronautica in Italy would build the center fuselage sections and horizontal stabilizer. Kawasaki Heavy Industries in Japan would build the forward fuselage and main landing gear wheel wells. Mitsubishi Heavy Industries would build the wing. Fuji Heavy Industries would build the center wing box. Spirit Aerosystems in Wichita, then formerly Boeing's own facility, which is once again owned by Boeing, would build the forward fuselage. Vought Aircraft Industries in Charleston would build the aft fuselage sections. Boeing's Everett factory would simply snap these massive sections together, install interiors, and roll out finished aircraft. The company projected that final assembly would take just 3 days. 3 days! Compare that to the weeks required for traditional aircraft assembly. It sounded revolutionary because it was. Boeing was fundamentally redefining its role in aircraft manufacturing. The company that had built the B-17, the 707, the 747, aircraft that defined American aerospace dominance, was becoming an integrator and assembler rather than a manufacturer. But here's what Boeing's leadership either didn't understand or chose to ignore. Aircraft manufacturing isn't like assembling consumer electronics. You can't simply hand off engineering drawings to suppliers and expect them to deliver flight-ready sections. The integration challenges are immense. Systems have to communicate, software has to be compatible, parts have to fit together, with tolerances measured in thousandths of an inch. Aircraft manufacturers had always maintained tight control over design and production, precisely because aerospace integration is brutally complex. Engineers need to be co-located, problems need to be identified and solved in real time. You need institutional knowledge built over decades. Boeing was giving that up. It was distributing critical engineering expertise to suppliers who had never built complete aircraft sections before, suppliers who were geographically scattered across continents and time zones, suppliers who would be using different design software, different manufacturing processes, and different quality control standards. The hidden assumption underlying the entire strategy was that these suppliers could handle systems integration without Boeing's direct oversight, that they could coordinate with each other across vast distances, that they could deliver sections that would simply bolt together. Boeing was betting that manufacturing aircraft had become commoditized enough that anyone with the right tools and drawings could do it. It was betting that the company's role could shift from builder to assembler without losing critical capabilities. It was betting that 70 years of manufacturing knowledge could be replaced with contracts and coordination. By 2007, it was becoming painfully clear that Boeing had bet wrong. The consequences of this decision would nearly destroy the program, cost billions of dollars, and permanently damage Boeing's engineering culture. What Boeing discovered was something the aerospace industry had known for decades, but somehow forgotten. You can't outsource knowledge, you can't contract away complexity, and you absolutely cannot build an aircraft by committee when that committee is scattered across the planet. The 787 was about to teach Boeing that lesson in the most expensive way possible. In October 2007, Boeing announced the first delay. The 787's maiden flight would slip, delaying first deliveries by 6 months. Then, in January 2008, another delay. Then April. Then a machinist strike and another delay in November. By 2009, the program had been delayed multiple times, pushing the first delivery nearly 3 years behind schedule. What was happening inside Boeing's supply chain was nothing short of catastrophic. The first crisis emerged in Italy. Alenia delivered the initial center fuselage sections to Everett for final assembly. Boeing's engineers opened them up and discovered a nightmare. Thousands of fasteners, the rivets and bolts holding the composite structure together, had been installed incorrectly. Wrong sizes, wrong torque specifications, wrong locations entirely. Every single fastener had to be removed and replaced, manually, by hand, on sections that were supposed to arrive ready for final assembly. Then the Japanese partners delivered their sections. The wing boxes didn't mate properly with the center fuselage. Gaps existed where precision fits were required. Wiring harnesses didn't match the interface specifications. Systems that were supposed to plug together simply didn't. Boeing discovered that suppliers were using different versions of the same CAD software. Design changes made in Seattle weren't propagating to partners in Japan. Italian engineers were working from drawings that were months out of date. Nobody's data was synchronized. The system's integration problems went deeper. The 787's electrical system was vastly more complex than any previous Boeing aircraft. The all-electric architecture meant miles of wiring, replacing pneumatic and hydraulic systems. That wiring had to be installed inside composite fuselage sections before they were ever shipped to Everett. But the suppliers didn't have Boeing's institutional knowledge of how to route electrical systems. Wiring bundles were too tight, creating chafing risks. Connectors didn't align. Software controlling different systems couldn't communicate because suppliers had made independent choices about protocols and interfaces. Boeing had assumed that detailed specifications would be sufficient, that suppliers could execute to those specifications independently. What it discovered was that aircraft integration requires constant communication, immediate problem-solving, and institutional knowledge that exists in engineers' heads, not in documents. The company's response revealed just how badly it had miscalculated. Boeing began flying Tiger teams, groups of experienced engineers around the world to supplier facilities. These teams would identify problems, develop fixes, and supervise rework. Boeing engineers were essentially doing the integration work that suppliers were supposed to handle. In some cases, Boeing had to take over entire sections of work. It sent hundreds of engineers to partner facilities for months at a time. It installed Boeing managers to oversee supplier operations. It was, in effect, rebuilding the vertical integration it had deliberately dismantled. The financial hemorrhaging was spectacular. Development costs that Boeing had projected at roughly $10 billion eventually exceeded $32 billion. The risk-sharing model that was supposed to distribute costs had backfired completely. Boeing was now paying to fix supplier problems while also compensating partners for delays. Launch customers were watching their delivery dates evaporate. All Nippon Airways had ordered 50 787s, with planned delivery starting in 2008. They were building their entire long-haul strategy around the aircraft. Japan Airlines, United, Air Canada all had made fleet decisions based on Boeing's promises. Every delay cost Boeing credibility, penalty payments, and order cancellations. Some customers switched to the Airbus A350, which Airbus had launched in 2006 specifically to compete with the 787, learning from Boeing's outsourcing mistakes before they fully materialized. Others simply walked away. Inside Boeing, the crisis triggered executive departures. The commercial airplanes division leadership changed. The 787 program manager was replaced twice. The company's stock price suffered as investors realized the program's problems weren't temporary setbacks, but fundamental failures of strategy. The deeper problem was becoming impossible to ignore. Boeing had outsourced not just manufacturing, but critical engineering knowledge. It had assumed that detailed specifications could replace hands-on expertise, that coordination tools could substitute for co-location, that contracts could enforce what only culture and experience could deliver. What Boeing learned, at a cost of tens of billions of dollars, was that aerospace manufacturing is incredibly complex. You cannot distribute that complexity across disconnected organizations and expect it to integrate seamlessly. The knowledge required to build aircraft exists in relationships, in tacit understanding, and in the ability to solve problems collaboratively, in real time. Boeing had tried to reduce aircraft manufacturing to a supply chain optimization problem. The 787 proved it was anything but. When the aircraft finally achieved first flight in December 2009, more than 2 years late, the problems were far from over. The first serious warning came in November 2010. ZA002, the second 787 test aircraft, was conducting a routine test flight when an electrical panel in the aft equipment bay caught fire. Smoke filled the cabin. The crew executed an emergency landing in Laredo, Texas. Investigators found that the fire had been caused by foreign object debris left inside the panel during manufacturing, combined with a poor design that allowed electrical arcing. Boeing fixed that specific problem, but it was a symptom of something larger: the rushed integration and quality control issues that permeated the entire program. Then came the batteries. The 787 used lithium-ion batteries, the same chemistry as laptop computers and electric vehicles, to power critical systems. Lithium-ion offered higher energy density than traditional nickel-cadmium batteries, saving weight and space, but they also carried risks. If damaged or improperly managed, they could overheat, catch fire, or even explode. During flight testing, Boeing experienced multiple battery incidents: overheating, smoke, thermal runaway events where the battery temperature spiked uncontrollably. Each time, Boeing and battery supplier GS USA developed fixes. Each time, the FAA accepted those fixes and allowed testing to continue. The 787 received type certification in August 2011. All Nippon Airways took delivery of the first production aircraft in September. After 8 years of development, 3 years of delays, and more than $32 billion, the Dreamliner was finally entering commercial service. For 15 months, the 787 operated without a major incident. Airlines were adding routes, passengers were praising the cabin comfort, Boeing was ramping up production. The nightmare seemed to be over. Then, January 7, 2013, a Japan Airlines 787 was parked at a gate at Boston Logan International Airport, empty, connected to ground power. An auxiliary power unit battery in the aft electronics bay began to overheat. Within minutes, it was smoking, then burning. Airport firefighters responded to find the battery had gone into thermal runaway, reaching temperatures of over 500 degrees Fahrenheit. The battery was supposed to have multiple layers of protection, monitoring systems, thermal management, containment. All of them had failed. 9 days later, an all-Nippon Airways 787 was climbing out of Yamaguchi, Japan, when the pilots received a battery fault warning. Smoke began entering the cockpit. The captain declared an emergency and diverted to Takamatsu Airport, executing an emergency landing with fire trucks standing by. This wasn't a parked aircraft, this was an active flight with passengers, smoke in the cockpit, a battery fire at altitude, the exact scenario that certification was supposed to prevent. On January 16, 2013, the same day that the ANA 787 had diverted to Takamatsu Airport, the FAA made an unprecedented decision. They issued an emergency airworthiness directive, grounding the entire global 787 fleet. Every aircraft. 50 planes operated by 8 airlines across 3 continents, all grounded indefinitely. It was the first time the FAA had grounded an entire aircraft model since the DC-10 in 1979, and unlike the DC-10, where the problem was clearly understood, Boeing and regulators couldn't definitively explain why the 787's batteries were failing. The investigation took months. Boeing, GS USA, the FAA, and the NTSB conducted exhaustive testing. They eventually concluded that the root cause was likely internal short circuits within battery cells, combined with inadequate containment and monitoring. The fix wasn't elegant. Boeing couldn't redesign the batteries themselves, that would take years. Instead, they added a steel containment box around each battery, with a venting tube to exhaust any smoke or gases overboard. They added more robust monitoring and control systems. Essentially, they assumed the batteries might fail and engineered around that assumption. The FAA approved the fix in April 2013. The 787 returned to service after a 4-month grounding. But the reputational damage was profound. The world's most advanced airliner, the aircraft that was supposed to represent the future of avionics, had been grounded worldwide because Boeing couldn't prevent its batteries from catching fire. While the 787 was still grounded, Boeing was already executing another strategic gamble that would compound the program's quality control problems. In 2009, Boeing announced plans to open a second 787 production line in North Charleston, South Carolina. The official reasoning was sound, adding production capacity to meet demand, creating geographic redundancy, and establishing a presence in a business-friendly, non-union state. The unofficial reasoning was more complicated. Boeing's relationship with its Seattle area workforce had been contentious for years. Multiple strikes, constant labor negotiations. The company wanted leverage. Charleston offered that leverage. Right-to-work laws, lower labor costs, and a state government eager to offer tax incentives. Boeing invested billions in the Charleston facility. They built massive factories, they hired thousands of workers, and they began producing 787 fuselage sections and eventually complete aircraft. But Charleston had a problem. The workforce was new, not just new to Boeing, new to aircraft manufacturing entirely. They didn't have the institutional knowledge that existed in Everett, where some workers had decades of experience building 747s, 767s, and 777s. The knowledge gap began manifesting in disturbing ways. In 2014, a worker discovered metal shavings, foreign object debris, inside the wing of a 787 being built in Charleston. Then tools, then entire sections of scaffolding. Workers reported finding debris in fuel tanks, in electrical bays, in areas where any loose object could cause catastrophic failures. Whistleblowers began coming forward with allegations that went beyond simple mistakes. They described production pressure so intense that quality inspections were being rushed or skipped entirely. They reported managers pushing workers to sign off on incomplete work to meet delivery schedules. They described a culture where hitting production targets mattered more than getting the work right. One former quality manager, John Barnett, testified that he'd found clusters of problems on Charleston-built aircraft, missing or improperly installed fasteners, debris contamination, incomplete electrical work. His concerns were allegedly dismissed by management focused on production rates. Boeing denied the allegations. It pointed to FAA oversight and its own quality systems. But the pattern was undeniable. Charleston was struggling with quality controls in ways that Everett, despite its own challenges, was not. The cultural difference was stark. Everett's workforce had built some of the most complex aircraft in history. They understood that aerospace manufacturing demands precision because lives depend on it. Charleston's workforce was learning that lesson in real time, under immense pressure to match Everett's production rates. Boeing's goal was to reach 14 aircraft per month across both facilities, but ramping production while maintaining quality proved nearly impossible. The company faced constant tension between quantity and safety, between delivery schedules and proper manufacturing processes. By the late 2010s, the FAA was increasing oversight of Charleston operations. Inspectors were finding defects that should have been caught during production. Boeing had to implement additional quality checks and slow production rates. The Charleston facility represented everything that had gone wrong with Boeing's strategic thinking. The same cost-cutting mentality that drove the outsourcing disaster was now driving geographic arbitrage and labor cost reduction. The same prioritization of financial metrics over engineering excellence was creating quality problems that threatened passenger safety. The 787 was finally becoming profitable, but Boeing's corporate culture had fundamentally changed, and those changes, they were about to produce consequences far worse than production delays or battery fires. By 2018, the 787 program was finally approaching break-even. Boeing had delivered nearly 800 aircraft by the end of the year. Airlines were ordering more. The production system, despite its ongoing challenges, was functioning. The Dreamliner had become the backbone of long-haul fleets worldwide. But inside Boeing, something had broken that couldn't be fixed with engineering solutions or production improvements. The cultural transformation that began with the McDonnell-Douglas merger, resulting in the 787's outsourcing strategy, had metastasized throughout the company. Financial engineering had replaced aerospace engineering as the driving force behind decision-making. Cost reduction had become more important than technical excellence. Meeting Wall Street's quarterly expectations, it mattered more than maintaining the institutional knowledge that had made Boeing the world's premier aircraft manufacturer. The 737 MAX program made that transformation brutally visible. When Boeing decided to re-engine the 737 to compete with the Airbus A320neo, it faced a choice. It could design a clean-sheet aircraft, expensive, time-consuming, but technically optimal, or it could modify an existing design to save money and accelerate the schedule. Boeing chose modification, or rather, was forced by an American Airlines order in 2011. It opted for larger, more efficient engines on a 50-year-old airframe. Those engines changed the aircraft's aerodynamics in ways that required software compensation. That software, the Maneuvering Characteristics Augmentation System, or MCAS, was designed to make the MAX handle like the previous 737 variants under specific flight conditions. But MCAS relied on a single angle of attack sensor. It could activate repeatedly without the pilot's awareness of the system, and Boeing didn't adequately explain the system to airlines or regulators because doing so would have required additional pilot training, which would have undermined the MAX's competitive advantage. The parallels to the 787 were impossible to miss. The same cost-cutting mentality, the same prioritization of schedule over safety, the same assumption that engineering problems could be solved with shortcuts rather than proper design, the same regulatory capture that allowed Boeing to essentially certify its own aircraft. When Lion Air Flight 610 crashed in October 2018, followed by Ethiopian Airlines Flight 302 in March 2019, killing 346 people, the world's view of what Boeing had become was affirmed. The MAX was grounded globally. The FAA's credibility was destroyed. Boeing's reputation collapsed. The 787 and the MAX were products of the same corporate culture. The difference was that the 787's problems manifested as delays, cost overruns, and battery fires. The MAX's problems killed people, 346 of them. The financial outcome of the 787 program tells one story. Over 1,230 aircraft had been delivered as of November 30th, 2025. The program will ultimately be profitable. Airlines love the aircraft. Passengers prefer it, the technology works, but that financial accounting misses what Boeing actually lost. It lost manufacturing expertise that took decades to build. Engineers who understood how to integrate complex systems left or retired. Their knowledge never transferred to the next generation. The supply chain partnerships that had defined Boeing's competitive advantage were fractured or destroyed entirely. It lost regulatory trust. The FAA's relationship with Boeing, once characterized by mutual respect and technical collaboration, became adversarial. International regulators stopped automatically accepting FAA certification. Boeing now faces scrutiny that adds years to development timelines. Case in point, the 777X. It lost the engineering culture that had produced the 707, the 747, and the 777. The institutional belief that technical excellence mattered more than quarterly earnings. The understanding that aerospace manufacturing demands precision because lives depend on it. Airbus learned from Boeing's mistakes. When it launched the A350 to compete with the 787, it maintained much tighter control over suppliers. It kept critical engineering in-house. It prioritized technical maturity over schedule. The A350 entered service on time, without major incidents, and has been remarkably successful. The 787's troubled development also reshaped Boeing's approach to future programs. When Boeing launched the 777X, a larger, more efficient derivative of the 777, it pulled back from the extreme outsourcing model. More engineering stayed in-house. Supply chain partnerships were restructured with tighter oversight. Boeing had learned, painfully, that you cannot outsource institutional knowledge. But the damage to Boeing's competitive position was already done. The A350 captured market share the 787 should have owned. Airbus now had a modern, efficient wide-body family, spanning from the A330neo through the A350-1000. Boeing's response, the 777X, has faced its own delays and certification challenges, a direct consequence of the regulatory scrutiny the MAX crisis had triggered. Even China was watching and learning. Comac's C929 wide-body program, developed in partnership with Russia, which was eventually dropped due to its sanctions over its illegal invasion of Ukraine, deliberately adopted a more conservative approach than Boeing's 787 gamble. Comac could be using proven aluminium-lithium alloys alongside composites, not betting everything on unproven materials at scale, and its proposed C939, a potential competitor to the 777X, represents China's long-term ambition to challenge Boeing and Airbus in the wide-body market that the 787 helped define. The 787 story isn't just about one aircraft program. It's about what happens when a great engineering company decides that engineering isn't actually that important, when institutional knowledge is treated as a cost to be eliminated rather than an asset to be preserved, when the people making strategic decisions don't understand or don't care about the technical complexity they're managing. Today, over 1,000 787s are flying. They're connecting cities that never had direct flights before. They're demonstrating that composites can work at scale. They're delivering the efficiency and passenger comfort Boeing promised. The 787 achieved its technical goals. It proved that composites could work at scale. It validated the point-to-point long-haul model. It forced Airbus to develop the A350 and pushed the entire industry toward greater efficiency. But the cost was nearly destroying the company that built it, and the competitive advantage Boeing sought, being first to market with composite wide-body technology, was squandered by delays that let Airbus catch up with a better executed program. The 787 Dreamliner represents aviation's most profound paradox. It achieved everything Boeing promised: revolutionary materials, unprecedented efficiency, and transformative passenger comfort. The aircraft works, the technology is proven, the market has validated the design, but Boeing nearly destroyed itself in the process. The core tension isn't between innovation and execution, it's between engineering excellence and financial optimization. Boeing's leadership believed they could reduce aircraft manufacturing to a supply chain problem, that institutional knowledge could be replaced with contracts, and that decades of expertise could be outsourced without consequence. They were catastrophically wrong. What the 787 revealed is that aerospace manufacturing remains irreducibly complex. You cannot distribute that complexity across disconnected organizations and expect seamless integration. You cannot prioritize cost reduction over technical capability without eventually paying a far higher price. Passengers love the 787. Airlines depend on it. The aircraft has fundamentally changed long-haul aviation, but Boeing lost something that may be impossible to recover: the manufacturing DNA and safety culture that made them the world's premier aircraft manufacturer. The question facing Boeing now isn't whether the 787 was worth building, it's whether the company can rebuild what it lost, or whether the damage has become permanent. So, here's what I want to know. Was the 787's success worth the risks Boeing took? Can a company recover institutional knowledge once it's been deliberately dismantled? Drop your thoughts in the comments. Hey, before you go, the YouTube algorithm thinks you're going to like this video next, so why not check it out?